In previous videos I have tried to describe Gibbs free energy, which is the basic understanding of one part of the science of corrosion studies. Corrosion is an electrochemical reaction. That means that there has to be electrical energy, there has to be metal, and there has to be an electrolyte, which is a chemical. If you take away any of these parts, corrosion stops. So, when we use cathodic protection to control corrosion, we control the electrical energy and we balance that so that no electrical energy flows from the anode of the corrosion cell into the electrolyte, and therefore the corrosion stops. We must be able to measure at which point we have stopped corrosion. When we examine the current methods of measuring corrosion control, measuring cathodic protection, we find that the system that is proposed does not and cannot work. I have made many further videos that actually demonstrate that the present system of measuring cannot work because the science is incorrect. When I discovered that this was a fact, I realized that we needed a method to ascertain the point at which we had balanced the equilibrium between the energy in the environment and the energy output, or EMF, of the anode of a corrosion cell. The laboratory arrangement for this measurement is described in DIN 50918, and I knew that we had to conform in the field with the principles of DIN 50918, or we could not measure corrosion in the field. After many months of experimentation, I devised a method which is now being called the Alexander cell, and it was called this by Tim French Mullen, a very well-established corrosion engineer who worked at the time for Corrosion Cell, which was then one of the leading providers of cathodic protection staff. The Alexander cell consists of electrodes or coupons. There are 3. This is cut from a steel bar, as you see, and it is cut into this shape, and that contacts the ground, and this contacts the pipe for the second part of the measurement. This is an electrode, and it is in contact with the ground, and this is an electrode which is on the top of the Alexander cell, and you will note that there is insulation between these two electrodes. We could call these electrodes coupons because they are offcuts of metal similar to that metal that is the pipeline under investigation. So we have here a corrosion cell which is put together like this, and this is a solid insulating material, and these are set inside this to keep them into position. The arrangement is that this surface, these two electrodes or coupons, are in contact with the ground, and this coupon, whoops, got it the wrong way round. This coupon is polished, and this coupon, which is the top one of these, is never polished, and therefore, because we know that polished steel is anodic to old steel, we know that when this is into contact with an electrolyte, with the same electrolyte that this is in contact with, the charges, the electromotive force created by the corrosion reaction on this coupon will pass into the electrolyte, which is bridging the two, and this current will then go into a meter. Oh dear, should have had the meter here. Right, into the meter, be measured, and come out of the meter into the bottom plate, and from the bottom plate it will then pass into the ground electrolyte and back into this plate to complete the circuit. And this is following the laws of science. Faraday wrote that the amount of metal that goes into solution at the anode of a corrosion cell is directly proportional to the amount of current that passes into the electrolyte as a result of that metal dissolving. Gibbs free energy says that there can be no such thing as zero energy. So wherever energy is taken away, energy from the universe, free energy, then passes into that void of energy to fill the gap. Therefore, there can never be negative energy. There can only be positive energy filling the void where energy has left. And this explains the corrosion circuit. The corrosion circuit in this case of the Alexander cell is from the anode to the cathode, through the meter, to the coupon at the base, into the ground electrolyte, and back into this solid metal, and that completes the circuit in obedience to all of the laws of science and the laws of electricity. We have Kirchhoff's laws, which tell us how much current flows into and out of a node in any circuit. We have Ohm's law, which tells us that the E, which is the amount of energy, is equal to IR, which is the current and the resistance. So we have these laws so that we can actually calculate what is going on in a corrosion circuit. And the Alexander cell enables us to actually measure the current and the potentials at the interface between the electrolyte and the metal. So this fulfills the need that is what needed in cathodic protection work. There is no other way. Okay, so now let's get to the actual manufacture of the Alexander cell. This one I made, I don't know, maybe 3, 4, 5, 6, 7 years ago. I don't know. I don't know when I made this, but I've been using it for experiments and demonstrations, and it has been used in the field for demonstrations. Okay? This one was made by an engineer recently, and I have tested this one and it works. So now I will show you how we test it. We have a meter here. Whoops. Let's try. How do we open this? Oops. Which we set on ohms. And this means, I don't know, I hope you can see this because I'm working alone here, so I cannot see what is being filmed. I can only hope that it is filming the meter and the readings and everything. Bloody, oof, that was difficult. Right, now this shows that each of these is electrically separate from each other. So this Alexander cell will work. There is no current passing through it at the moment because it hasn't been charged up. There is no reaction at all on here to feed the circuit. So in order to test the reaction, evaluate the reaction, we have to go to this setting, which shows there is not very much reaction. There is very little, whoops, there's none, no. These damn clips are so difficult. These are crocodile clips and they are so fierce that an old guy like me, ow, damn. Right, this is dreadful, not very professional, never mind, doing the best I can. Right, now you will notice that there is no current flowing between here and round the circuit. In order to prime this, we need to polish the anode because we know that polished steel is anodic to old steel. There is no current now because the circuit isn't complete. So what we have to do is we have to say, right, we have to make a wet patch so that the charges can travel from the bottom plate to this bottom plate of that, and we then have to bridge the top coupons or electrodes or whatever you want to call them. And hopefully you will see there is now a corrosion current which is flowing from the polished anode into the old steel. Hopefully you can see that. See, I can't see I can't see the camera view from here. I'm trying to do this all on my own. Now you will notice that when I take this off of here, the current will stop. I will put it back. And the current starts again. If I lift this, the current will stop again. Put it back, and the current will start again. So we know that this Alexander cell actually works and actually measures corrosion current. Now, the engineer that made this one made another one which he gave me a couple of days ago, and I will now test this new one to make sure that it actually works. So in order to test it, we have to put it onto dry ground. Whoops. Try. And we have to set this on ohms. And what this does, there is a, God damn it. Right, there is a 9-volt battery in the meter, and that sends a charge, a 9-volt charge, through here, through the circuit to return here, and you can see that there is more resistance than 20 mega ohms resistance in this unit. Therefore, the engineer made this unit correctly. Now we will put this onto microamps, and there is virtually no current flowing because it is on, the circuit is not complete because it's on dry electrolyte. It's like desert sand. So we will now put some wet electrolyte there, and there is no current flowing because there's no current flowing between here and here. And I will now put electrolyte bridging the gap, and we see that there is current flowing from the polished, well, actually he polished it, I haven't polished it yet. If we take this off and I then polish it, put this back on again, and you will notice the current is flowing. And if I take this off, the current stops. And if I lift this up, the current, oh, it hasn't stopped because it's stuck to the bottom. Current stops. Put this back down. Oops. And the current starts again. So this Alexander cell is working, it's properly made, and it's functional, and we will put it in a box with all the kit and all the instructions, and we will sell it. Okay, so that has completed what I intended to do for this particular video.